We know more about the surface of the moon than the bottom of the ocean. Autonomous underwater vehicles, or AUVs, are helping us change that. Here's how. Autonomous underwater vehicles are transforming the way we explore and monitor the oceans. Whether they're mapping the seafloor, inspecting offshore infrastructure, studying marine ecosystems, or conducting defense-related surveys, AUVs rely heavily on high-performance optical components to operate effectively in one of the most demanding environments on Earth. Working at depth is incredibly challenging. Visibility is limited, light levels are low, and pressure increases rapidly. That's why many AUVs use optical domes, which are carefully engineered hemispherical windows that allow wide-angle imaging and sensor coverage without introducing distortion. These domes maintain clarity while withstanding extreme hydrostatic pressure, ensuring cameras and LiDAR systems can capture accurate, undistorted data even thousands of meters below the surface. In addition to domes, AUVs frequently use flat windows for forward-looking cameras, lighting systems, and laser-based sensors. Flat windows are ideal where a narrow, well-controlled optical path is needed. But to survive deep water deployment, they must be manufactured from pressure-resistant materials like sapphire or thick fused silica. These materials combine high mechanical strength with excellent transmission across visible and near-infrared wavelengths, ensuring that optical quality is maintained under heavy loads. To maximize light throughput, which is critical in a low-light underwater environment, these optics are finished with anti-reflective coatings. Standard optical surfaces can lose a significant amount of light to reflection, but AR coatings minimize these losses, improving image quality, sensor sensitivity, and overall system efficiency. They also help reduce back reflection into lasers or detectors, which is important for systems like structured light scanners and underwater LiDAR.
AUVs rely on optical systems that deliver clear imaging and accurate sensing in one of the harshest environments on the planet. At depth, pressure rises, light levels drop, and seawater introduces distortion, scattering, and abrasion. To overcome this, AUVs use specialised domes and windows designed to protect internal sensors while maintaining performance. Optical domes are essential because their geometry naturally reduces refraction-induced distortion. As a spherical surface, a dome ensures that incoming light rays strike at consistent angles, allowing cameras and LiDAR systems inside the vehicle to maintain accurate fields of view across wide angles. This is important for applications like navigation and seabed mapping, where small distortions can lead to significant errors. AUVs also rely on windows, which act as pressure-resistant barriers for forward-looking cameras, lasers, and lighting systems. These windows must withstand extreme forces while preserving optical performance. The material choice is highly important. Sapphire is often used for its strength and scratch resistance, allowing operation at high pressures without cracking or clouding. Fused silica, on the other hand, offers high optical clarity and low absorption across UV, visible, and near-infrared wavelengths, making it ideal for imaging and sensing tasks that require high transmission. To maintain optical efficiency underwater, these components are finished with specialised coatings. AR coatings ensure high transmission, improving the performance of cameras and laser-based sensors in low light conditions. Additional protective coatings enhance resistance to abrasion, saltwater corrosion, and particulate impact. AUVs are essential tools for exploring, monitoring, and maintaining subsea environments. They can operate independently without constant human control, giving them the freedom to reach places that are difficult, dangerous, or impossible for divers or remotely operated systems. One of their main applications is in offshore energy inspection. AUVs are used to survey subsea structures like oil platforms, wind farm foundations, risers, and mooring lines. Their ability to run long missions with high-resolution cameras and optical sensors allows operators to detect corrosion, marine growth, and structural damage early. This reduces downtime, cuts inspection costs, and significantly improves safety. AUVs also play a major role in defence. Navies deploy them for mine countermeasures, harbour security, underwater reconnaissance, and mapping unknown terrain. They are ideal for covert data collection, and their autonomy reduces the risk to personnel in hazardous waters. In marine research, AUVs enable scientists to map the seafloor, track marine life, measure water chemistry, and monitor climate-related changes in the ocean. AUVs can dive thousands of meters below the surface, enduring pressures far beyond human limits, providing insights into regions that have never been seen directly. Another use is pipeline monitoring. Subsea pipelines transport oil, gas, and critical utilities across vast distances. AUVs routinely inspect these lines for leaks and damage, helping maintain supply and preventing environmental contamination.
In subsea environments, reliability is everything, and that starts with the right components and the right partner. From prototyping through to production, we offer stable lead times, scalable pricing, and the technical support needed to ensure your systems perform even in the most demanding conditions.